So now in the project J, when we talk about the pulse generator, you see, everything that you've been learning about the debouncing filter can be used again, right? Here, for example, for adapting the start-stop button, all right? And so QA is going to be a perfectly right pulse in the frequency of 200 Hz. The problem here is that you have, the frequency selected for the physical phenomena, which is the sampling of a button, okay? And that frequency is specific, whatever it is, 100 Hz or 200 Hz, that is because of the physical phenomena. And it is the same thing if you have to sample audio, right? If you have to sample voice, for example, you will pick up a 8 kilohertz sampling frequency. Or if you have hi-fi in mind, it is going to be 44.1 kilohertz, the CD quality, right? So the signal, the physical phenomena that you like to digitalize is demanding a very specific frequency. That is the point. And on the other hand, after sampling the signal, you've got something digital. So this something digital has to be connected, for example, to a dedicated processor or a microprocessor that is going to have naturally another frequency, probably much higher. For example, 100 kilohertz in this exercise or 100 megahertz, okay? So the point is exactly this one, how to connect two circuits that are going to work forcefully using different clocks, how to connect them and in which way, okay? How can you go interfacing circuits that are designed for different frequencies? So in one way you have, for example, here in the left, the discussion about the bouncing filter alone, right? So if you think about this picture, this is going to be the expected timing diagram for the debouncing filter, okay, without anything else, okay, as if it had to work alone. So in this case, what you've got here is the frequency clock debouncing squared that is ticking and is generating sampling periods. So you are sampling once and then something obscure or not defined, and then you are sampling zeros. And for example, in this way that we've done that in the debouncing filter example, after detecting three consecutive zeros, we are going to have a very perfect digital pulse that is going to last for 5 milliseconds. So this is, or if that were the case, if QB was to be used, it is going to be very similar, another digital pulse at the same time, with an acceptable delay from the event, 3 clocks, you may say, or 4 or 5 clocks, that's okay. And then you have a pulse that is going to last as long as you have the key clicked, okay? So this is the way it works if it has to work alone. However, in this application, the things are more complex because you are using this clock, that is what you see here, you see the 200 Hz clock, the debouncing filter clock in one hand, and on the other you have the high frequency clock, probably the system clock. So how to combine both analyses, or how to analyze a circuit like this, which is synchronous because both frequencies, both clocks are from the same clock generator, and that's a great advantage because both of them are going to be synchronous, but they are at a very different time scale. You see 5 milliseconds here period, and here 10 microseconds period. All right, so how can you go interfacing this or analyzing this in the case of by means of a timing diagram? Well, because here, for example, what you've got from the dedicated processor point of view is the requirement of being able to store, to record the QA pulls, right? And so that the machine can start if this is the start button, or later on the machine can be stopped if the same pulse is interpreted as the stop button. So what you are requiring here is a 1-bit memory cell. And this 1-bit memory cell, for example, is convenient to be an RS flip-flop or a GK flip-flop, right? That's the one that is going to be convenient for this idea of memorizing or storing one pulse until it has to be used. Because you see, the control unit, when the pulse is going to be used, after using the pulse to start the process or to stop it, the machine will clear the memory cell by means of a signal to control the reset input of the flip-flop. Okay, so in one way the QA is going to set the flip-flop, set high the start button, and on the other hand the control unit is going to send another pulse for resetting the flip-flop, you see, and perhaps something else, like the debouncing filter itself, because there is no need to keep the QA high anymore, because the pulse has been acknowledged by the control unit, and it can start the process or it can stop it. So that's the picture, okay? It is not a simple picture. So what we can do here to study this situation is to talk about the timing diagram associated to the debouncing filter, but now let's go and zoom around the important event, which is here above everything else, the detection of the rising edge in QA. So you can go and zoom this specific time, and now consider the situation of this QA. This setting of QA from 0 to 1, you can consider that from the perspective of the system clock, right? That's the point. So in principle, QA is stated to last 500, pulses of the system clock. But let's see if this is really what happens in the end or not. And to do that, you have to have this analysis here, talking about everything together, talking about the debouncing filter, which is going to be the source of QA, talking about the control unit, because the control unit will evolve and sometimes will generate the reset signal and the like. Okay, so let it be like this. You may very well generate vertical lines of time, and this is the point where something is going to happen. So if you start the analysis, for example, at this rising edge, okay, at this rising edge here, a value in QA has been detected, even if it goes high, right? Doesn't matter, because it's a synchronous system. So a 0 is detected here. So because of the reset that came from the control unit is 0, you have 0, 0. So in a problem like this, it is understood that this is an RS flip-flop. So the Q in the future, if you have 0, 0 sampled, you keep the value, right? So nothing happens. So the output of the flip-flop is kept high, because if you have 0, 0, you see, this 0 is kept for another 10 microseconds period. And now let's see what happens. Because now, the QA is already high. So a 1 is detected now. So what you've got here is the perfect situation of a set. You see, when you have 0, 1, you are saving a 1. And when you have 1, 0, you are saving a 0. That's the way it works. So this is what happens here exactly in this rising edge. You have a 1 in set and a 0 in the reset. So the output of the flip-flop goes high that way, okay? And is kept high for a period. So the thing is that at this time, because the control unit works with the same system clock, you know, at this time, what the control unit is sampling is a 0. So if the control unit was still idle, now is yet idle for another period, right? So nothing changes. But in the next clock age, the things may be different. For example, the QA is still high, the clear is still low, so it's again a repetition of generating another pulse for another period, another high level value for another period. You see, the output from the flip-flop is kept high, but now, you see, the control unit can sample for the first time, you know, a 1. So if a 1 is sampled, this means that the control unit can start the process of, you know, generating the frame of 16 pulses and then the consequent delay, if that is what is predicted if by means of a periodic signal. So the first thing that the process does, you know, is to generate the low data state. There is a jump here from idle to low data, and then another one, because now the process is not going to be depending anymore on the start button, because the process has already started. Okay? So now in the low data, if you see the configuration of the control unit state diagram, okay, in the low data, nothing happens in relation to the clear flip-flop. But in the next one, in the pulse counter enable, yes, there is a clear flip-flop that goes high and then it goes low. So here you have a pulse. In this state, pulse counter enable, you have a clear flip-flop signal. So this has to be indicated here in the diagram. First, in lower data, nothing happens, but then in the pulse counter enable, you see you have the pulse. Very well. But you know that this pulse is generated by the finite state machine, that is the control unit, but it is generated some nanoseconds later. All right? So what is the meaning of this? Well, this clear flip-flop pulse is attacking, is driving, you know, the clear direct of the clear direct, you know, of the debouncing filter. So automatically, when this signal goes high, the QA synchronously goes down, you see? So whatever, so instead of being high for 5 milliseconds, accordingly to this interface, the QA is set high only about, you see, 30 microseconds. That's all that it lasts QA. It goes down because it's connected to the clear direct. All right. So let's see what happens with the flip-flop now. Let's see what happens with the flip-flop. Okay, because now you have again a 1 sampled and a 0 sampled. So nothing happens. You still are rewriting another one. So for another period in the output of the flip-flop, you still have a 1. Okay? But in the next state of the control unit, you go to another state that is called, it has a name, load shift register, okay, with the P, the 16-bit value. This is what you do in the next state of the control unit. But here, you know, the signal clear flip-flop is 0. So you've got this pulse in the end. And this pulse, you know, is sufficient because now at this time, you see, is sampled correctly as 0 and 1. So this means that you've got a reset. And this means that the output of the flip-flop goes synchronously down. That's the way it works, okay? So that's the idea of starting the process of the control unit by means of detecting, first of all, generating a clear digital signal corresponding to the process or to the phenomena of clicking a key, and then saving it as long as it is acknowledged, you see. This means if the control unit is generating the clear flip-flop signal, in this state, this means that the machine acknowledges the QA value. So it can be reset again, and the system can be prepared from now on while the machine is shifting bits, or later on when the machine is delaying time, 1 second, 2 seconds, and the like, whatever. If you click again the button, you will get another QA value high until it is acknowledged by the machine. Okay, so that's the way it works, and that's the way you may like to explain, the configuration of a synchronous system that is going to work with two different synchronous clocks from very different frequencies. So it's about, first of all, a study around one of the frequencies, and then you make zoom in a given transition, because you can see it better, absolutely, because they cannot be placed in the same diagram. Logically, if you are solving this in the model sim or in the active EETAC simulator, it's going to be the same idea, but you can use the mouse to zoom to the given location in time and see this kind of dynamics. All right, so you see the circuit alone works in one way, okay, but when connected to another circuit, because this circuit drives the clear direct, for example, the behavior of the debouncing filter changes. Okay, that's the point, and this is something difficult that has been left to the end, and you may imagine that as a plus, something extra that is here for you to pay attention on it, right?